Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on graph theory, lecture number 17, in which I will give the concept of weighted graph and Dijkstra algorithm. Firstly, I will discuss about weighted graph. With the help of particular example, we shall try to understand that what is a weighted graph. Let A, B, C, D and E be some cities. We have connecting roads between some cities. AE be the connecting road between A and E. Similarly, AB be the connecting road between A and B, AC be the connecting road between A and C, BC be the connecting road between B and C, ED be the connecting road between E and D, and DC be the connecting road between D and C. Since AE be the road connecting two cities A and E, let the length of the road is 25 kilometer and length of this road is 20 kilometer. Length of this road is 35 kilometer. Length of this road is 22 kilometer. Length of this road is 28 kilometer. Length of this road is 27 kilometer. Therefore, we see that we have cities A, B, C, D, E, and we have connecting road between some cities. Now, let us assume cities to be the vertex of a graph and connecting roads to be edges of the graph. Therefore, this picture is a graph having vertices and edges. But it is given that each edge has its length. Some non-negative real number is assigned to each edge. Therefore, a graph in which each edge is assigned to a non-negative real number, then that graph will be called a weighted graph. Now, this graph is called weighted graph. Now, we write the definition of a weighted graph. Definition of weighted graph. A graph in which a non-negative real number is assigned to each edge of the graph, then the graph is called a weighted graph. The number assigned to each edge E is called the weight of the edge E and is denoted by W under bracket E. Now I will describe about Dijkstra algorithm to find the shortest path from a single source. Before giving the theoretical description of Dijkstra algorithm, firstly I will give a particular example for describing the working process of a Dijkstra algorithm. Now let we have a weighted graph. Here vertices are A, B, C, D, E, F, and each edge is assigned to a non-negative real number. Now we find the shortest path of different vertices from a given vertex. The given vertex is known as source. Let source be A. Now we write here source A, then we write vertices B, C, D, E, F. Since the shortest path from A to A is 0, so we will not write this number 0. And initially we write the distances of other vertices from A is infinitive. Now we find the vertices adjacent to A. The vertices adjacent to A is B, C, and F. The shortest distance between A and B be 7. Here under B we write 7. The shortest distance between A and C is 9. Shortest distance between A and F, here F we write 14. Since other vertices are not adjacent to A, so here we write infinitive. Here we select the smallest number. The smallest number in this row is 7, and we enclose this 7 by a square. The distance between A and B is 7, that is shortest path from A to B is 7. We write here star because we select this vertex B as secondary source, and from this vertex B we will write the distances of the adjacent vertices. Since adjacent vertices of B, B, D, C and A, already we have the source A, so we do not write for A, we will write for D and C. As distance from A to B is 7, here 7. For C, we write the distance from A to B and then C. From A to B the distance is 7, so we add 7 with distance 10, and the 7 plus 10 equal to 17, and previously it was 9, the distance from A to C. So we take minimum of these two numbers, minimum, and that is 9. So here we write 9. Now the distance from B to D is 15. Already distance from A to B is 7 here. So we add 7 plus 15. Here 7 plus 15. And here infinitive. We take minimum of these is 22. So here we write 22. Since vertices E and F are not adjacent to B, so we write the same number, infinitive and 14. Here we write 7. Here we write A, comma B, as in this row the B be the secondary source. And now we take minimum of these numbers, as already 7 has been selected. This is called the stable vertex, because distance from A to B has already been calculated 7. This asterisk denotes that distance between A and B. Now we select the smallest of these numbers, 9, 22 and 14. Here 9 is the smallest number. This is for C, and we enclose this by square. Now we select this by giving asterisk. Here we start to calculate distance from C to its adjacent vertices. Adjacent vertices are D and F. As distance from A to C, here C, 9, because already I have told that the asterisk mark denotes the distance from A to that vertex, means A to C, 9. A to C is 9. Now we find the distance of vertex D from A via C. Here 9 plus 11, here 11, and here D 22, previously it was written 22, so 22. So we take minimum of these two numbers, means 11 plus 9 is 20. So we write here 20. Now vertices adjacent to C is also F, and here we have number 2. Already A to C is 9. 9 plus 2. 9 plus 2, 11, and previously distance was 14. Minimum of these equal to 11. So here we write 11. E is not adjacent to C, so we write the same number. Now here we write 7, here 9, here we write A, B, and secondary source is here C. Now we select minimum of these numbers, as already these vertices were selected, B and C. These vertices are called stable vertices because shortest distance from A to these vertices have already been calculated. Now smallest number is 11. This is for vertex F. We select this and enclose this by square, and we write here star. Now we calculate distance from vertex F to its adjacent vertices. Adjacent vertices of F are A, C and E. Already A and C were selected as stable vertex. So we find the distance of vertex E from A via F. So here 9, already it was 11, and 11 plus 9, and previously it was infinitive. We take minimum of these. Minimum of these is 11 plus 9 is 20. Here we write 20, and we write other same. Now it is a stable vertex already selected. Now we have 20 and 20. Both number are same. So we may select any of this number. Let we select this number 20. This is below D. So we select the vertex D. The vertices adjacent to D be B, C and E. Already B and C were stable vertices. So we get only one vertex E. We have to find the shortest path from A to E via D. Already D 20 and here 6. 20 plus 6. 26, and earlier it was 20 E. We have to find minimum of these. Minimum of these is 20. So below E we write again 20, and this was selected in this case. So we write here square with star. These vertices are all stable vertices. Here we write A, B, C and F. Here D. We write A, B, C, F, D. We write other same. 7, 9, 20. This is 20. Already we have found this. Here 11. Now remains only one vertex E. Here we have 20 single number. So we select this, and we have no vertex to find the distance from E. So here we write A, B, C, F, D, E. Now shortest distance from A to B is 7, A to C is 9, A to D is 20, A to E is 20, A to F is 11. This row denotes the shortest path from A to different vertices. Now we have to find the shortest path from A to different vertices. Now, firstly, we find shortest path from A to F. A to F. Firstly, we write here A and F lastly. Here we see 11, here also 11, here also 11. This 11 star comes from this star, means 9. This is C. So we write here C, and this C9 and this comes from A. So path is A to C to F. This is the shortest path. From A to F. Now we find the shortest path from A to E. Firstly, we write here A, here E. Here we see 20 below E. This 20 here same. This 20 comes from this 11. This 11 is F. Here we write F. And this 11 comes from this. This is C. So A to C to F to E. Now we find the shortest path from A to D. Here we write A, here we write D. This is the shortest path. Here we see below D 20. This 20, this 20, this 20. This 20 comes from this 9. 9 is below C. So we write here C, and here same, and this comes from A. A to C to D. This is the shortest path from A to D. A to C is 9 and 9, C to D is 11. 9 plus 11 equal to 20. Now, shortest path from A to C. Here we write A, here we write C. Here we see number 9. This 9, this same, this same, this same, this same. So, this is the shortest path, A to C. And similarly, A to B, the 7, 7, 7, 7, 7. A to B, shortest path is A to B. And in this way, we may find the shortest path using Dijkstra algorithm very easily. We may find the distance of the shortest path from a source A to any vertex D, and also detect the shortest path like this. Now I will give the theoretical description of Dijkstra algorithm to find the shortest path from a single source. Let G be a simple weighted graph and let the length of an edge from ith vertex to jth vertex be Dij. If ith vertex is not adjacent to jth vertex, then we assume Dij equal to infinity. We have to find shortest path from a given vertex A to any other vertex. The vertex A is said to be source vertex. Since the distance from vertex A to vertex A is 0, so initially we write the distance of A is 0 and distance of other vertices infinity. This process is called leveling of the vertices. Therefore, vertex A is leveled with 0 and other vertices are leveled with infinity initially. This type of leveling is called temporary level. Initial leveling is called temporary level. Now we will find the vertices adjacent to vertex A and label them by following process. Here, let vertex A is denoted by ith vertex. The name of the vertex A is ith vertex. Let. Then every jth vertex gets a temporary level by the formula. This is the formula. Minimum of old level of jth vertex. We will label the jth vertex. Then formula will be minimum of old level of jth vertex and old level of ith vertex plus Dij. This is the formula for labeling of jth vertex. If ith and jth vertex are not adjacent, then Dij equal to infinity. The smallest value among all temporary level is detected and this becomes the permanent or stable vertex. The vertex which has the smallest level during this process becomes a stable vertex. In the next step, by taking stable vertex as source vertex, initially we have assumed the vertex A as source vertex. Now the vertex which has minimum value of the level becomes a source vertex. This is called secondary source. And we proceed as before and consequently we may get another stable vertices. The level of stable vertices are shortest paths from initial source vertex to these vertices. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.